My name is Johannes Kloos, and I will be giving a talk on asynchronous liquid separation types. This is joint work with Rupak, Majumdar, and Viktor, Vafeiadis. So let me first introduce you to the model of asynchronous concurrency. So I'll give you an example of an asynchronous execution. We have here a task A, which starts executing, executes a few commands, and after a while it forks off a computation that runs in a task B by performing an operation that we call post B. Now this computation doesn't start at once, but it's put into a buffer to be executed later. And after this post operation, task A continues to execute. After some more time, it also posts a second task, let's call it C. Here's a post C. We have task C that's also put into the task buffer, and A continues to execute until it terminates. Now we have two tasks in a buffer, B and C. And since this task terminates, we now run a scheduler that chooses one task, which in this case task C, which is supposed to continue. So this one runs for a while and decides that it needs the results of task B to continue. So it can run an operation wait B. That causes the scheduler to run. We choose task B, let that continue until it's finished, and then return control to task C, and that continues to run after that. So the key idea of this model is that you have some kind of cooperative concurrency where tasks run until they either yield control by waiting or terminate. This kind of concurrency model turns up in a surprising number of places, or at least very closely related models. For example, the model used by Ajax in web applications is similar, where you basically have the events that are generated by Ajax and different website event handlers. The Android programming model with its event queues is quite similar. And interrupt handling operating systems surprisingly has something like this. So for example, Linux, there's the concept of a bottom half, where inside an interrupt handler, you can create a small task to be run later, and they are queued up like this. So what we consider here are programs using asynchronous concurrency written in OCaml. And I have a small example program that I'll now explain to you. So what we do here is we want to copy data from an input stream to an output stream. First, we create a task using the post operation, which reads from the input stream, and wait for this task to complete. This yields a buffer, which contains the data that we've read from the stream. And after that, we create another task to write it out, wait for it to drain, and copy more data. The reason for using asynchronous concurrency here is that normally you could basically create a new task for the read and the write operations, which just runs in the background as asynchronous I/O, and you can schedule yourself away while the I/O is running and have some background tasks to work. So finally, this continues until we reach the end of file. Our question was, how can we reason about such programs? So since we're using OCaml, the obvious thing to try is to use the type system somehow. And there are two challenges now. One is that we need to type asynchronous code. So if you just consider a small code fragment, post, read from the input stream, where we can assume, for example, that read is just a function that takes a stream as an argument and returns a buffer. In that case, we could type the whole thing as it returns a promise to a buffer, where a promise is, as usual, something that says, as soon as this fragment of code is executed, you have you can get the result of this execution to, you can basically wait for the result of this execution. It's the future or promise or whatever you want to call it. So this is pretty straightforward. We can actually do a bit more. We could introduce subtyping. Say we have a subtype of buffer called init buffer, which says the buffer is initialized in some way, it contains valid data. As it turns out, if you type read, takes a stream as an argument and returns an init buffer, then it's perfectly valid to type post of the read int as a promise to an init buffer. And actually in the paper, we do a bit more. We use not just simple subtyping, we use refinement typing in the style of liquid types. So far so good. This looks pretty easy. But there's a second challenge, and that is typing programs with mutable state. So assume, for example, we have another copying loop now, which instead of having a buffer created by the read function, uses a buffer that's on the heap. And for now, let's consider a version without concurrency, just to see what's going on. So the changes here are that the main copying loop now gets a pre-allocated buffer. The read and the write operation get that buffer as an argument to do the I/O, and we create a new buffer to do the copying. So the question is, can we again use subtyping to ensure that only initialized buffers are ever written? So we don't use the freshly allocated buffer, write that to disk, but actually wait for it to be read first. And actually this turns out to be more tricky. So let me give you an example why simple subtyping and mutation don't mix well. So here's a small piece of our camel code. For those not familiar with the syntax, I'll quickly say what it means. So the ref in the 0 in the top means we create a new reference to an integer, initialize it with 0, and assign it to r. The next time we assert that the content of r, so exclamation mark r is 0. We update the contents of r to 1 and assert that r is 1. Now, can we prove using the type system that these assertions hold? So basically, can we compile them away to using just type information? Well, we could just try to do something with subtyping. Assume we have two singleton types, int equals 0 and int equals 1, which are both subtypes of int, meaning that the integer here is exactly 0 or exactly 1. It would be nice if we could just use this information to prove that the assertions always hold. The thing is, the only thing where we can basically try to choose a type here is the type of r. There's three ways we could type it. We could type it as a reference to integer. Turns out this is perfectly valid, but we can't prove anything. If we say that it's a reference to 1, then this is actually wrong, because initially it will be a reference to 0, and vice versa. So this approach would probably not work. The thing is, what we need here is what we call strong updates, where we actually have something in the types that tells us how the heap changes. The expression comes from static analysis, where you also want to track the exact contents of, say, the heap or something. Now, outside of type systems, this is actually a very well-studied and well-solved problem. For example, we could look at program logics. Let's assume the program is annotated with some kind of separation logic-like notation. So here we say that initially the heap is empty. After creating the reference, it contains a 0 that stays around until we change it to 1. After that, it contains a 1. Using this information, it's actually perfectly straightforward to prove that the assertions always hold. So the question is, well, it would be nice to have both of these things, right? Let's summarize what we have. Subtyping and refinement types are pretty expressive. And in the guise of liquid types, we can actually get strong automation. So we can automatically derive refinement types. But they don't deal with mutable state out of the box. On the other hand, we have program logics. And these are good at dealing with mutable state, as we've just seen. They're also good at dealing with concurrency. I haven't shown that, but we'll come back to that later. But in their case, automation is much, much harder. So it would be good if we could just combine both. And our contribution is that we actually show a way of combining type systems, namely refinement types, and program logics to reason, in our case, about OCaml programs that have both mutable state and asynchronous concurrency. More precisely, in the paper, we show how to combine liquid types and a fragment of concurrent separation logic. We call the result asynchronous liquid separation types. For the rest of the talk, I will use a more simplified version. So if you don't know what liquid types or concurrent separation logic are, that doesn't matter. I'll show you something simpler, which gives you a flavor of the whole thing. In the rest of the talk, I will mainly talk about how the type system works. Towards the end, I'll also talk a bit about how we perform type inference for this type system, also mentioning some limitations, and describe a few of the examples that we've looked at to validate that our type system is useful. So let's start with the type system. We considered an example again. So this is the example from before, the copying loop which uses pre-allocated buffers. And we actually just, for the most of this chapter, look at how we type the reading from the input stream to the buffer part. So before I show you how to do this, I have to go back a bit and remind you of how typing judgments normally look like and how we change them. So in a traditional typing judgment, we have three parts. We have the environment, which basically says what types the free variables the program have. We have the expression we want to type, and we have the type that is assigned. And they're written down like this. What we add is a precondition and a postcondition. The precondition stating that when we type the expression, we assume that this condition holds on the heap, and the postcondition saying what holds after executing the expression. So for our example, so the read data from the input stream to the buffer bit, the classical typing roughly looks like this. We have in our environment the input stream in S, which is a stream. We have the buffer, which we type as reference to some basic buffer type. And we say that the whole thing returns unit, because that's what these things usually do. We assume that we don't get any data, we only have the side effect. So now to actually say what the contents of the buffer are, we have to add pre and post conditions that will look like this. We have a precondition, which says that there is some heap size mu, which points to contains a value that we can type as buffer in the given environment. Also, we have a post condition that says, like, after reading this data, so executing this expression, this heap size mu will now contain a buffer which has a type init buffer, so it is initialized in some sense. Now the question is, there is this mu now, where does it come from? Well, obviously, if you look at how the read works, it should somehow be related to the buffer buff. This we do by adding an index to the reference here, which says that this is actually a reference to heap size mu. Note also that now suddenly we are allowed to do subtyping when talking about heap, because we put it in pre and post conditions. And this actually turns out to be sound. We can actually do even more now. So we can now talk about mutable state, but we were coming from a concurrency angle. And it turns out that we can handle this quite easily now. So let's consider a modified fragment of the code. We not just read from the buffer, but we create a task to read from the buffer, so we post it. So we know what the type of the reading piece looks like. We know how this should be. And for the post expression, the type works like this. We assume the same environment, and we say that the precondition is the same. Mu points to some buffer. Now, what should the type and the post condition be? Well, for the type I already implied this at the beginning. There should be a promise that says, if you finish executing this task and get its return value, it should be a unit. So we say it's promise of unit. And you may notice that there's now an index pi that I'll need in a second. For the post condition, we use an idea from concurrent separation logic and introduce a so-called wait permission. And the wait permission means the following. We know that once the task is finished executing, the contents of the heap size mu will be an initialized buffer. So there is the mu points to init buffer bit again. But we only know that this is true once the task has finished running. So we wrap it in this wait statement and say, you will receive this resource once you have waited for this task to complete. And now the pi appears again to tie it back to the promise we have. Okay. So now let's look what it looks like in a complete example. We use a slightly modified version of the example I started with. So instead of just reading and writing from the buffer, we create tasks and wait for them immediately to do the reading and writing so that we don't block. So the reading expression, we've just seen how that should type. Actually, in practice, you would have to have type for the function read as well. And as you can see here, this is a pretty long type. You don't need to look at all the details, but we have pre and post conditions at that now. Posting the whole thing gives us the same type that we've just seen. So we have a precondition that that the heap cell mu must exist. It contains something of type buffer. We get the promise again that we get a unit, and if we wait for that task, which is the non-name pi, we can break open the wait permission and get an initialized buffer. And actually, if we type the whole expression with the wait in front of it, this is just what we get. Now, combining this with the read and the write would give us this type. So we would keep the buffer initialized, because the writing doesn't change anything. The whole inner part of the loop actually has this type now. We say that there must be some heap cell mu that contains a buffer. The loop body doesn't return anything. And interestingly enough, now we say that the post condition must be heap cell mu must exist and be a buffer. Why is that? Well, if you look at the first line, it says like, if the input stream actually has an end of file condition, we do nothing. And if we start from an empty input stream, we actually never read anything into the input buffer, So actually its type will not change. Finally, if we type the whole thing, our statement will be that the type of this will be, we start from an empty heap, and if we execute the function body, well, we get a unit value because we only want side effects. And now there is a new heap cell mu pointing to a buffer. Okay, so far so good. I'll show you some more interesting examples of this later. But let's now first look at how type inference works here. So type inference in this case means that we have two inputs. We have an OCaml program using these new primitives post and wait. And we have the types of the external functions. So this is where we add annotations. We annotate all external functions. We can then run LST type inference on it and get the type program in the style that we've seen just now. Okay, so how do we do this? And for this I have to explain quickly how liquid types works, because that's how what we base our work on. So the idea in liquid types is that you want to create, that you want to calculate refinement types for an ML program, meaning you have normal types, but they, that are also annotated with predicates. And how they do it is that first start with basic ML typing. And after this, you have a fully annotated program. So each sub-expression has a type annotation. From this, you can generate constraints that say how the subtyping relations between the different expressions should look like. You solve these, what we call refinement constraints, and instantiate them. And now you have an OCaml program that's typed with refinement types. What we did for ALST, so as opposed to liquid separation types, is that we basically use the same procedure and augment it a bit. So first of all, in this step where we create constraints, we add a new type of constraints that we also generate. It's what we call resource constraints. These describe basically how the pre and post conditions of the different sub-expressions are related. And it can be seen as some kind of control flow graph where the edges are annotated with the operations that change the state of the heap or create and wait for tasks. Additionally, we introduced two new steps into the procedure where we solve one type of constraints, namely the resource constraints, and instantiate the resources, meaning the pre and post conditions. And at this point, we basically have the same setting as in the liquid types, where we have types that still contain type variables from refinement constraints and a set of refinement constraints. And just to mention how this works, for the solving of the resource constraints, we use an abstract interpretation-based approach. At this point, I think it's also useful to mention that there are some fundamental limitations to this approach. So one problem that we have is that we currently have no way to express pre- and post-condition polymorphism. So for example, here is a very standard function from the ML standard library, the iteration function on lists, which basically just executes a function on each list element in turn for its side effects. And as it turns out, In the type system as it stands now, we cannot provide a single useful type for this. The problem is that the pre or post condition of the iteration function would actually depend on those, on the pre and post conditions of the function f that we give in. So this is a problem that we cannot usefully deal with higher order functions as of now. In the examples later on, we actually had a workaround. So we always considered partially applied versions of things like iter and map, so we monomorphized them, and now could actually talk about the effects. Another thing that we cannot handle right now is unbounded task creation in the following sense. So assume we have another function that traverses a list, creates a task for each list element. That is something we cannot usefully express right now. Okay, now that we've seen how type inference works, I'll mention a few of the examples we have looked at. So in the paper we have a set of examples. We have, again, the copying loops. We have some more variants of that. We have one rather complicated one that has double buffering. We have some from the revert or camel book and so on. But more interestingly, we have two big examples. One is coordination code for a parallel SAT solver. So what we did there is we took an example from X10 that shows how to build a parallel SAT solver where you have several worker threads that independently try to solve a SAT formula, and every so often they will basically poll each other to see what the others have done and incorporate that operation, that data into their own operation. We built a simplified version of the part that does the coordination and used Asynchronous liquid separation types to show that the specific invariant always holds, namely that the result that this function computes will always be true if and only if the formula is set, assuming that the worker threads are correct. And finally, the example I'm going to talk about for a minute or two is that we looked at code from the MirageOS system. So MirageOS is an operating system written in OCaml, and we took part of its file system code, a very old version though I have to say, and tried what we could say about that code using our tool. And interestingly enough, the following happened. So here is an excerpt of the code. I'll explain that in a moment. Don't read it or anything right now, just see that it's there. I'll explain what happened with it. And then we just tried to run the tool to see what happens. We got an error. So it said that access to resource size something that is wrapped in a wait permission. What does that mean? Well, first of all, it actually means that this code has a race condition. And now let me tell you how we found that error and what happened here. So in this code, we have, first of all, a state type up there, which contains, amongst other things, a mutable field, FAT, I think, yep. So what this means is that in this FAT file system, there is one data structure, the file allocation table, short FAT, that is consulted a lot in doing file system operations. So if you want to read a file, you have to look at that table. If you want to write data, you have to look at the table. If you want to find where a directory is, you have to look at it, and so on. For this reason, this code caches it so that it doesn't have to continuously load it from disk. Now, there is a function to do an update on the file system. That's the one given at the bottom. And amongst other things, it does the following thing. If you write an update to this file system, you also have to update the directory of the file that you're updating to set access times and so on. So that's what it did. And after that, it updated the cache copy of the FAT inside it. Now, if you actually look at what this update directory function does, you dig through several levels of function calls, and at some point, it posts a task. And that one uses that cache copy of the FAT to do some deeper magic. I'm not going into that, but it read that thing. Now, if you look at this bit of code and stare a bit harder, you may notice that this task is posted but never waited for. So actually, you have a task hanging around that uses data from the cache copy of the FAT. But this task is hanging around while we modify this data. So actually this data could get out of sync here. So this is actually a bona fide race condition because this task will stay around for a while. You could modify the on-disk version of the table quite heavily. And this would actually use some outdated data here. Okay. So it turns out that in newer versions, they fixed that by completely getting rid of the asynchrony. They're doing all the reads and writes synchronously now. Okay. So let's sum up what we've done. So I have shown to you asynchronous liquid separation types. What they do is they allow us to reason about OCaml programs that have been augmented a bit with asynchronous concurrency and mutable state. These types are an extension of liquid types with ideas from concurrent separation logic. And we have shown that we can actually do type inference on that. So that's all I have. Thank you for your attention. I hope you have questions.
Okay, who wants to start?
So I suppose that there is what you were showing us can all be done through type inference, and therefore there is a price to pay in expressivity because.
Yes.
So how big is that price? Have you got any idea?
So one thing that's a really big problem here are the fundamental limitations I mentioned. The price you pay is that there are a good number of idioms out there that cannot be reasonably expressed right now. We cannot, for example, deal with higher order functions with effects right now. This is something that's simply not there. And that actually turns out to be a hard problem. Another thing we cannot properly express are programs that have, let's call it benign races, where, for example, implement a lock yourself, because that would just be detected as a race condition and wouldn't type. On the other hand, for the examples that we've tried, this seemed to be working reasonably well. You have to do some hand messaging for the code sometimes, for example, to get rid of polymorphism. But for the examples we've tried, it worked.
So if you run over a data structure and we are locking and unlocking, can your system prove that that's correct?
Right now, probably not. That would need an extension.
Hi, nice talk. I have, I think, 2 questions. So if I think about your work compared to the 2 prior works, I think you motivated very clearly the advantage you have over liquid types as before. So over separation logic, I mean, you have a nice framework now in which we can express what we want to do for a particular program such that you can do inference. So my first question is, to what extent is that similar to doing something like predicate abstraction for the separation logic problem in the original setup? And my second question is actually on the slide, so that's convenient. I didn't really see, I can understand with that model in mind, if that's accurate, why the first problem is an issue, and I didn't really understand why unbounded task creation is an issue.
Okay, so for the first question, how it relates to predicate abstraction. I haven't really thought about that yet, but you could basically see the types as some kind of predicates saying what could be in a certain heap cell or something. So that would be a possible way of seeing things. I'd have to think harder about this to actually say if it's a good model, but right now it's say it's a reasonable approximation. And the second question, can you repeat the second question?
My second question was, I don't have a good intuition for why your second limitation exists. I have a feeling, I have an understanding why you have trouble with the first example on the slide, and I don't understand why the second one is a problem.
Okay, so for the second, this is actually a problem about our types not being sufficiently expressive for this. The thing is, what we can express right now is a fixed number of, say, weight permissions or promises that are stacked or in a list. But in this case, you have unbounded number of these things. And there's right now simply no way to express this.
Okay, makes sense. I think that sounds like something you could maybe extend your work to, and
Yeah,
but I might be wrong.
yes.
The first problem sounds like a more substantial.
Yeah, the first one is more substantial. The second one you could maybe extend by using some kind of how you do it in recursive data types or with some folding structure or something. But there's some trickiness involved here.
Okay, thanks.
Could you compare your work with type state?
I must admit that I'm not familiar with type state.
There's a question over there.
Hi, so going back to the first limitation, is that more limitation of the separation logic part of the reasoning, that it cannot handle higher order stuff, or does it have to do with the refinement side?
It's more a type problem here. So the problem is actually that what you'd have to do is have some way to express how the pre and post condition of, say, the iteration function here depends on those of the function f that you pass in. And
what I mean is, does states have does references have anything to do with this problem? If you moved out references, would you be able to?
So if I get rid of the whole state thing here, I basically have only trivial pre and post conditions. And in this case, this is actually a solved problem because this is just higher order functions in standard ML-based, standard ML typing. So this is actually easy.
So follow-up question is, why did you set this work in OCaml? Like, why didn't you look at a C-like language and because both refinement types and separation logic is more fleshed out in those cases.
So this is basically this called for historical reasons. We had wanted to work on something for which we already had some level kind of tooling, and liquid types was out there, so we thought that it would make sense to look at OCaml, because there are programs written in this specific concurrency style, there are tools out there, and it seemed like a good idea at the time.
Any other questions? Okay, well then, thanks a lot.
Thank you.